Good morning, class. Today I'm here with the next lecture and next topic. To firstly, I will share the topic, and after that, I will explain this topic in front of you. As I discussed in the previous lecture about dependency, uh, I'm stopping my lecture on dependency. A plan an undrawn dependency relationship is sufficient for most of the using relationships. You will encounter, however, if you want to specify a shade of meaning, the UML defines a number of stereotypes that may be applied to dependency relationship. There are a number of stereotypes which can be organized into several groups. First, there are stereotypes that apply to dependency relationship among classes and objects in the class diagram. First thing is in the dependency bind. It specifies that the source instantiations the target templates using the given actual. You will use bind when you want to model the details of template classes. For example, the relationship between a template container class and an instantiation of that class would be modeled as a bind dependency. Bind includes a list of actual arguments that map to the formal arguments of the template. Derive specifies that the source may be computed from the target. You will use derive when you want to model the relationship between two attributes or two associations, one of which is concrete and the other is conceptual. For example, a person class might have the attribute birth date, which is concrete, as well as the attribute age, which can be derived from birth date. So, in is not separately manifest in the class. You did show the relationship between age and the birth date by using a derived dependency showing age derived from birth date. As you simply know what is the mean of derived, derived is come from the one another. Permit it specifies that the source is given special visibility into the target. You will use permit when you want to allow a class to access private features of another class, such as found with C++ friend classes. instance of instance of specifies that the source object is an instance of the target classifier, ordinarily shown using text notation in the form source target. Instantiate specifies that the source creates instance of the target. These last two stereotypes let use model class object relationships explicitly. You can use instance of when you want to model the relationship between a class and an object in the same diagram, or between a class and its meta class. Usually, however, this is shown using text syntax. You will use instant instantiate when you want to specify that a class creates objects of another class. Power type specifies that the target is a power type of the source. A power type is classifier whose objects are the children of a given parent. You will use power type when you want to model classes that classify other class, such as you will find when modeling databases. Refine. Refine specifies that the source is at a finer degree of abstraction than the target. You will use refine when you want to model classes that represent the same concept at different level of abstraction. For example, during analysis, you might encounter a customer class which during design you refine into a more detailed customer class complete with its implementation. Use specifies that the semantic of the source element depends on the semantics of the public part of the target. You will apply use when you want to explicitly mark a dependency as a using relationship in contrast to the shaded sets of dependencies other stereotypes provides. Continuing, there are two stereotypes that apply to dependency relationships among packages. A generalization. Generalization is a relationship between a general classifier called the superclass or parent and a more specific classifier called the subclass or child. For example, you might encounter the general class window with its more specific subclass, multi pan window with a generalization relationship from the child to the parent. The child multi pane window will inherit all the structure and behavior of the parent window. The child may even add a new structure and behavior, or it may override the behavior of the parent. In a generalization relationship, instances of the child may be used anywhere instances of the parent apply, meaning that the child is sub substitutable for the parent. Most of the time you will find single inheritance sufficient. A class that has exactly one parent is said to use single inheritance. There are times, however, when a class incorporates accepts of multiple classes, then multiple inheritance models those relationships better. For example, figure shows a set of classes drawn from a financial service application. The class asset has three children: bank account, real estate, and security. Two of these children, bank account and security, have their own children. For example, stock and bond are both children of security. This is an example, or we can say by the figure out what can we do. Asset is a class, and these three children's bank account, real estate, and security. Here, both two children's stock and bond and bank account have checking account and saving account, and here bank account interest bearing item, insurable item, real estate is an insurable item, multiple inheritance, single inheritance, and multiple inheritance. This figure shows how to the connection of the classes and their relationship are done and how the classes are interact with each other. Now moving to the two of these children, bank account and real estate, inherit from multiple parents. Real estate, for example, is a kind of asset as well as a kind of insurable item, and bank account is a kind of asset as well as a kind of interest bearing item and an insurable item. Some superclasses are only used to add behavior and structure occasionally to classes that inherit their main structure from ordinary superclasses. These additive classes are called meshings. They do not stand alone but are always used as supplementary superclasses in a multiple inheritance relationship. For example, interest bearing item and insurable item are mixings in figure. Use multiple inheritance carefully. You will run into problems if a child has multiple parents whose structure or behavior overlap. In many cases, multiple inheritance can be replaced by delegation in which a child inherits from only one parent and then uses aggregation to obtain the structure and behavior of more subordinate parents. For example, instead of specializing vehicle into land vehicle, water vehicle, and air vehicle on one dimension and into gas powered, window powered, and muscle powered on another dimension, let vehicle contain a means of propulsion as a part. The main downside with this approach is that you lose the semantics of substitutability with these subordinate parents. Now moving to the association. An association is a structural relationship specifying that object of an thing are connected to object of another. For example, a library class might have a one to many association to a book class, indicating that each book instance is owned by one library instance. Furthermore, given a book, you can find its owning library, and given a library, you can navigate to all its book. Graphically, an association is rendered as a solid line connecting the same or different classes. You use associations when you want to show a structural relationship. There are four basic adornments that apply to an association: a name, the role at each end of the association, the multiplicity at each end of the association, and aggregation. For advanced uses, there are a number of other properties you can use to model subtle details such as navigation, equalification, and various flavors of aggregation. Association classes. In an association between two classes, the association itself might have properties. For example, an employer employee relationship between a company and a person. There is a job that represents the properties of that relationship that apply to exactly one pairing of the person and company. If it would not be appropriate to model this situation with a company to job association together with a job to person association that would not tie a specific instance of the job to the specific pairing of company and person. In the UML, you did model this as an association class, which is a modeling element that has both association and class properties. An association class can be seen as an association that also has class properties, or as a class that also has association properties. You rendered as association class as a class symbol attached by a dashed line to an association line, as in figure. Association classes, here is the example, and so many times I will explain about association. Here, association, company and person. Between the two classes, company and person, what is the relationship? We can say association class dotted by job description, date hired and salary. This is the association between both company and person. Job is a class and job is associated with the person and company. This will show in the association class in this manner. No, sometimes you will want to have the same properties for several different association classes. However, you cannot attach an association class to more than one association, since an association class is the association itself. To achieve that effect, define a class and then have each association class that needs those features inherit from C or use C as the type of an attribute. Now moving to the realization. Realization is a semantic relationship between classifiers in which one classifier specifies a construct that another classifier guarantees to carry out graphically. A relationship or a realization is rendered as a dashed directed line with a large open arrowhead pointing to the classifier that specifies the contract. Realization is different enough from dependency, generalization, and association relationship. That is, that it is treated as a separate kind of relationship. Semantically, realization is somewhat of a cross between dependency and generalization, and its notation is a combination of the notation for dependency and generalization. You will use realization into two circumstances. First, in the context of in interface, and in the second is in the context of collaboration. These are two circumstances where we use the realizations, and realization is different, as I explained, from dependency, generalization, and association relationship. Most of the time you will use realization to specify the relationship between an interface and the class or component that provides an operation of service for it. An interface is a collection of operations that are used to specify a service of a class or a component. Therefore, an interface specifies a contract that a class or component must carry out. An interface may be realized by many such class or components, and a class or component may realize many interfaces. Perhaps the most interesting thing about interface is that they let you separate the specification of a contract the from its implementation. Furthermore, interfaces span the logical and physical part of a system architecture. For example, as figure shows, a class such as account business rule in an order entry system in a systems design view might realize a given interface such as rule agent. That same interface rule agent might also be realized by a component such as accounts rule in the systems implementation view. Note that you can represent realization in two ways: in the canonical form using the interface stereotype and the dash directed line with a large open arrow head, and in an elided form using the interface lollipop notation for a provided interface. This is an example which show the relation of interface. As I told in different manners, this show the realization. Here is a dotted line and this one is a arrow. This show the relationship of account business rule with the interface I rule agent, add rule, change rule, explain rules, and conical form provided interface in the this form of system. So many types you can see, so many type of rules when you are going to design. These are the a part of the realization within the structure. You will also use realization to specify the relationship between a use case and the collaboration that realize the use case as figure shows. In this circumstances, you will almost always use the dashed arrow form of realization. Realization of a use case, validate user validation. When a class or a component realize an interface, it means that clients can rely on the class or component to faithfully carry out the behavior specified by the interface. That means the class or component implements all the operations of the interface, responds to all its signals, and in all ways follows the protocol established by the interface for clients who use those operations or send those signals. Thank you, class. Now moving to the next topic. Next topic will be explained in the next class. Uh, I will be explaining about UML class diagram and their types. So still I will stop here. Today's session is completed. Again, I will explain in the next lecture. Thank you.